Hey guys. So let me share the screen with you so we can start the lecture today. So would you please let me know if you can see the slides? Perfect. So we'll just wait a few seconds here so people can join the lecture. So how's everybody doing? It's getting there, huh? We're getting there, right? Those are 2 weeks. Yeah, thanks for asking. Everything is okay. Yeah, I hope it wasn't a very bad experience in fluid mechanics. Okay, let me jump into the topic. As I mentioned last time, this will be the last chapter that we will have analysis problem or problem analysis on this topic. The last 2 chapters will kind of an overview of the material, like some kind of a quick summary of what is open channel flow and the flow in the boundary layer stuff. But this chapter will be like, the last chapter that you really need to solve problems on. Okay, so last time we talked about the centrifugal pump, if you remember, and we covered a very important difference between the positive displacement pump and the hydrodynamic pump. And we actually focused more onto centrifugal pump for this reason. And if you remember, we presented 2 types of performance curve for this pump. For the positive displacement pump, the pump has to operate in order for the fluid to move outside in the delivery side, like pushing the fluid out. And I think we had some discussion with some of your friends after the lecture about how the pressure is built up by the resistance of the fluids. I think this is very important concept to understand that the pump is a device to push fluids, right? So in this case, if you have this pump is connected to a long line which has many resistance, the pump will be able to overcome these total losses by increasing the pressure at the outside port of the pump. We call it the delivery side. Okay, and in this case, if you disconnect the pipe, and you start measuring the pressure at the exit of the pump, you will not see the same value of the pressure. So the pressure actually at the exit of the pump is dependent on the losses in the line, depend on how much the pump is resisting. So for a positive displacement pump, the pump has to operate and the fluid has to be, going outside of this pump no matter what, right? For the hydrodynamic pump, we said there might be possibility of having the valve at the end, at the exit side of the pump that is completely closed, right? And you still see the pump is running, operate, or the impeller or the rotor inside the pump is running, while the pressure increased to a certain limit, and that's it. And that's why you will see at in this side here, you'll see that the flow rate is 0, and the pressure here max out at a certain point, right? But for a positive displacement pump, this is not, it's a vertical line and it's going all the way, right? So if you, for example, if you close the valve for a positive displacement pump, you might see a damage in the system because of the pressure keep increasing, or even the motor that is driving the pump will be burned out, right? Because the pump cannot withstand a complete closure at the exits. And last time we stopped at this slide here when we talk about like, those type of performance curve of the pump are, are provided by the manufacturer, right? So for a centrifugal pump, we know that the centrifugal pump is something like this, right? So we have the rotor. This rotor is rotating using a motor, and all this inside a casing. Right. So the fluid will come in this direction, and then, right. So if you look at this from these sides, you will see like, sorry. Right. So this is rotating in this direction, right? So this is what we call it the impeller here, right? So you might expect like, some of these centrifugal pump can operate with variation on this impeller diameter. So this is what we call it the impeller diameter. So this is the impeller. And this is the diameter of this impeller here, right? So each casing of the pump or the manufacturer will design the pump that operate at a different, operating condition. Maybe this operating condition can be, different for a different RPM or the speed of these rotors. So, for example, here this is the N or the RPM of this, which is provided by the motor. So if you increase the speed of the impeller, you might, change the performance of the pump, and then you can basically like, achieve higher heads for maybe higher RPM or higher rotational speeds. Same thing if you are actually changing, the impeller diameter, of course, to a certain limit. So within a certain, variations, right? So the casing that is designed by this manufacturing will accommodate like, plus or minus some, different impeller diameter. And that's why you will see here in this curve, this is at the same RPM. So, same RPM, which means that all these curves are provided for the same rotational speeds, right? You see here the RPM here is like, 1170 RPM. Here, like, for the curve down, and the bottom of the page here is 710. So if for every single rotational speed, you will see a full performance curve of the pump. And even within the same speed, you can actually use a different impeller. And that's why you will see those line here, this line here for different diameter of this impeller, right? In general, the performance curve of the pump is taking this kind of shape. So if you look at any centrifugal pump, you will see the flow rate on the x-axis, the head of the pump. When, if you remember, the head of the pump is basically the difference between whatever coming as a pressure and what is going out as a pressure. So that we call it the manometric pressure, or the head increased by the pump. And people were asking why head, because if you remember back in when we start talking about like the Bernoulli equation and the hydraulic gradient line and all this, we manage in the fluid mechanics, when we are dealing with fluid flow, we manage to put everything, all the energy in terms of heads. So it will be much easier to add those values together and just presenting all the information in terms of head of fluid, right? So head here mean whatever the value of the pressure divided by rho g or gamma of the fluid. So in order to get like, the pressure heads. So this is a manometric pressure, and all the curve of the centrifugal pump will follow same kind of shape, right? So this is a relation between the manometric pressure and the flow rate. And this is all at same RPM. Okay, so for the 1 RPM, you will see this curve is going like this. Okay, so this is basically what we have. So for 0 flow rate, you still have a head that is basically not like infinity or not like so high, like it's going to be limited by a certain value for a centrifugal pump. If you change the speed, you will see this curve here. So this is N1, let's say, and this is N2 is less than N1. And if you change the speed higher, so N3 here is greater than N1, right? So the more you change the speed, the performance curve or the relation between the manometric pressure and the flow rates change, right? So, and then the other part of the, you know, the performance curve that we are talking about here is efficiency. So you will see here, this line here is representing constant efficiency line. Okay, so this line here is representing constant efficiency line. You can see here, this is 85%, this is 87. That means if there is a point here, that means it should be in between these two values as an approximation, right? But those lines are representing the point at which the efficiency is the same for every point here, right? Now, this lecture today, we're going to talk about like where the operating point of the pump when we put this pump in a system. So the system mean those piping, right? So we have a system that has many piping, and you know we need to move the the float from point A to point B, and we are putting this pump in, right? What will be the value for these flow rates, right? And if you remember, all what we are trying to explain in these lectures is how can you develop some understanding when you are selecting the side of the pump or selecting the motor that is driving this pump for a certain flow rate and overcome a certain losses in your system. Okay, there is another curve here that is called net positive suction head that we're going to talk about in the next few slides. Okay, but performance curve, efficiency, and flow rate head relationship. Okay. And for different RPM, you are expecting to see a different set of curves at these speeds. Okay, so when you're looking at pumping principles, so basically for a steady state condition, and this is most of the time for this course, we are only talking about a very simple fluid flow problem. So let's consider, for example, here a steady state condition. So the pump is already operating in the system, because the pump will take some time, once you start, the pump to operate. So to start from zero, but let's assume the pump is operating and the flow is moving in the system and everything is a steady state. So in this case, if we need to present the energy in, using Bernoulli equation, or the energy between point 1 and point 2. So we're going to talk about now, are we talking about the inlet and outlet of the pump versus the system, the total system that we are talking about. Okay. So let's consider only whatever coming from the pump. So the pump this is a pump here. So let's have this. This is a suction side, and this is a delivery side. Okay, so when I'm talking about here, I'm talking about this point 1 here and this point 2 here, right? So the flow is going like this. Okay, so whatever coming from the pump and going out at point 2. In order to look at the difference between the energy at point 1 and point 2, same thing using Bernoulli equation. We just put the pressure, and the velocity at point 1, z at point 1. All sorry, this is the difference here is energy 2 minus energy 1. Sorry. Okay. So all this pressure at point 2. Point two, or this is what we say, point 2, and the pressure at point 1 plus the velocity plus z. So this is all energy head, right? at 1, and this is all energy at 0.2. The difference between the energy at 0.2 and the energy 1 is basically what we need, the pump need to supply, right? So that's why you will say that this is equal to HS, right? Plus the losses, you know, that we have for friction inside these device here, or the pump here, right? So HS minus HF. So the net head is a primary output parameter for the turbo machine, because this is what we said, like, you know, most of these pumps are designed in order to provide this energy difference, or in the form of pressure increase or head increase. If you look at this, if you, for example, for a simple term here, if you assume the velocity 1 and velocity 2 are the same, Z1 and Z2 are very close, there is no variations. So at the end, the head or the energy difference is becoming a pressure difference. So this is where the idea of a pump as a device that is increasing the pressure came from, right? So if you neglect the difference between the potential head of Z1 and Z2 just before the pump and after the pump, this very small value. Piping actually changing in the suction versus the delivery. So the velocity in real life is changing, but if you assume this change is not too much, so that means the kinetic energy also is neglected. So at the end, you will end up with a head of the pump that is equal to delta B over rho g, and delta B over rho g is your head, the pressure head between 1 and 2, and sometimes we call it the manometric pressure head. Okay. Please interrupt me if you are if you have any questions as we are going in this. This is very important topic actually to many engineering applications. So, at some point of your life as an engineer, you will be dealing with system that is carrying, fluid, and is going to be a pump that is basically driving this fluid. Okay. So make sure that you, don't skip any of the stuff that you don't understand. So as I mentioned, delta B over rho, this basically your manometric pressure, or the manometric head delivered by the pump, right? And if you need to find out the power, if you remember what the power is, the power of the flow energy, remember the power or the flow energy or the power energy of the fluid. Remember the power is for a fluid flow is what? Anyone? Flow energy, flow power. Okay. I keep asking the same question every single lecture. Flow energy, flow power. What is the flow energy? Anyone here in this class? Anyone? Not sure. Can you at least say anything? Okay, volume times the pressure. And if I need to find power, will be flow rate, volume flow rate times power, right? So flow rate times power. So in this case, if I have rho GH, this is the pressure, times the flow rate, which is Q here, this will be the power. So the power required in order to drive this pump, we basically call it the power needed for moving this fluid in, by this pump. The power required to drive the pump is what we call it the brake power. Brake power, this is in general, or brake horsepower if you are measuring the power in horsepower, right? Brake power mean the power needed to just you apply on the the brake or the shaft that is rotating this pump. So this is whatever added to the pump in terms of energy in order to drive this pump. Okay. Brake horsepower, or the brake power here, is if you are talking about a motor that is driving the pump. So the pump here, and this pump is driven by motor. Okay, so this motor will provide a torque and also provide angular speed, right? So the motor actually providing this torque times omega. And this is what we call it, like, you know, the brake horsepower, or the power that is created from the motor. So we're not talking about the electrical power. So because here at the end, this will be like, you know, the power added, you know, this will be electrical, but the motor has a certain efficiency. So depend on the efficiency of the motors, the amount of power output of the motor will be the input to the pump. Okay, and the pump is going to be, you know, driving. Driving, you know, a fluid here from point 1 to point 2. So here, electrical motor, electrical power. This is brake power. And here is hydraulic power. Okay, you'll see here how it's converted, how this power is converted from the electrical side to you know, the hydraulic side of the thing, right? And the efficiency of the pump will be the input and the output are related by efficiency, right? So for a pump, the input here is brake power and the output here is hydraulic power, right? Or we call it the fluid power that we are talking about. So that's why the efficiency of the pump will be output, which is hydraulic power, or the flow power, which is rho g h times q, and then divided by the brake power. So this is a brake power, right? So if you wanna, you know, if you are using horsepower units, that means it's a brake horsepower, and here will be the hydraulic. Or this is a flow power here, right? Okay. So now for practical applications, in this case, you have a system that you need to run fluid in, and then you have a pump. I need to match these pump and the system, right? So most of the time you are dealing with system like this that consists of many components, right? Valve, elbow, entrance at the tank, you know, all these kind of, you know, components, right? And let me ask you just a simple question before we go here first. So here, let's say a tank here, and tank, if you remember, we talk about the tank as representing energy, right? Representing energy at point A. Okay, and I have a tank here. Okay, and this is point B. Okay, and now I have a system like this. Okay. Let me ask you a question. Now the system as it looks like on this picture here, where is the fluid will be moving from which point to which point? Why? Higher energy. I like that, right? So this is the energy here, right? And if you remember, we call it, this is our datum, right? And the level of the tank here, this is basically the energy head, right? So, you know, the energy head in this tank here is basically HA. And this tank here is the total head, right? The total HP, the energy head B, right? So the fluid will have to go in this direction, right? In order to move the pump, in order to move the fluid from A to B, I needed a device that is adding energy to the fluid that make it move from point A to point B, right? And that's why in this case, well, let's just erase this. And then I have a pump, and I'm gonna put this pump here, or sorry, let me just put it here, right? This pump here. And now I am, right? And basically this pump here is, of course, if I plot the hydraulic gradient line, if you remember the hydraulic gradient line, This is the line of the energy as you go. This is the energy is decreasing, right? So what will happen in the pump? So this is the total energy line. Energy is decreasing because of the losses. What once happened to the pump here, the pump will increase the energy, right? So if you look at this, I want to put it in a different color here. So the pump will increase the energy like this. And as we go, right, all the way, so the total energy line go all the way to match the level of the other tank, right? So what the pump is doing, the pump is changing the energy, right, from points just before the pump to the point after the pump. We call it H pump in this case, and the pump is pushing the fluid in the system. Okay. Z here, I think people were talking here about Z and potential energy. For a tank, this total energy is the head of the tank, right? So the point at any point inside the tank, the total energy is a potential energy, or like, you know, the hydraulic energy inside the tank. So if you can consider this at any point here, the velocity is 0. This is a pressure over gamma, and this is potential. So the total will be your line. So this is your total energy line inside the tank, and it is a horizontal because there's no motion inside, there's no losses inside the reservoir, as we say. But as the fluid is going inside the pipe, the energy will be decreased because of the frictional losses and eddy losses and so on. Okay, let me ask you now another question. Hopefully you're getting this right. So I have a tank like this. And this is point A. And I have a tank like this. This is point B. And I have a system like this. Okay. Okay, let me ask you a question. Where is the fluid will move in this case? Between point A and point B. Assume that this is your line, piping line. A to B. Okay. Did I make it maybe clear to everybody that this level almost the same? Won't move. Why? Why is not going to move? Same energy level, right? Excellent, right? Because same energy, that means the fluid is not going to move, right? So the fluid will be static in the system, right? Because there is nothing to drive the flow to overcome the losses in the system, right? Okay. So in this case, in order to drive the fluid, I have to do what? I have to do, you know, another pump here. So I have to basically put a pump here. And now it's all depend on if I want to drive the fluid in this direction or this direction, right? So it's up to me, right? So let's assume this is what is moving here, right? So what is the pump function here? So versus here, like, you know, here you are trying to lift, right? So the pump here is doing lifting here. You're lifting from point A to point B. Here, what the main function of the pump here? Not just starting the fluid, supplying fluids, right? Just making the fluid to circulate, right? So imagine I need to move these fluids, right? So I'm going to go here, right? And okay. So the fluid here is, the pump here is circulating. right? The main function here is circulate. Like, for example, give me an example here, like, the car, taking the oil from the casing inside the engine, move the oil inside all the engine part, and then bring the oil back into the same tank, right? So we're moving the fluid from tank A to tank A again, right? So in this case, the oil pump in any car is basically doing the circulation, right? So sometime we need to overcome the losses in the system here for a circulation purposes, right? So in this case, the pump is doing this circulation inside the system. Okay, let me just do one more thing here. Okay, I have a fluid, a tank A and tank B. And let me ask you first, where is the point the fluid will go from A to B, B to A to B, because of the energy difference, right? So the fluid is going like this. Okay, so the fluid already going between A and B. Okay, so why do you think, like, in many cases we'll put a pump here? Many application will put like a pump here. What is the main reason for putting the pump here between A and B? How about the fluid still moving here? Making it flow in the other, no, I'm not gonna move it in the other direction. The main direction is A to B. So I need the fluid to go like this. Yeah, can you adjust your, like, this language here, drain quicker? What do you mean drain quicker? Like, it's not draining here. How about not drain? What else? What quicker drain? Increasing the flow rate, right? So, right? So basically, you are trying to boost here, right? So this is boosting the flow rate. So the flow rate here in the beginning between A and B, it's only because of this energy difference, right? But when you have a pump like this, you are boosting the fluid, right? So you are basically increasing the energy of the fluid that move it even faster between A and B, right? So in this case, we are doing, right? So which means that every system, so just before putting the pump, we call this is a system. Like every time we are putting this dotted line on the piping system, this is your system. This is your actual system component that has losses, fractional losses, and so on. So when we are talking about this, so the system, right, if you are looking at the system here, the tank A and tank B, it is basically, the potential head, the pressure head, the V square over 2G, the kinetic head, plus all the losses, the fractional losses and the eddy losses, right? So for any system, just before putting the pump, right? So even without the pump, for any system, and the system here is a piping system. Okay, so between point A and point B, or point 1 and point 2, is going to be the static head here, right? Plus V square plus, right? And here, right, same thing, right? Or you can say this is H static A, and this is H static B, or the potential difference here, right? So for at any point here, right, the pressure is 0 at the point at the top, and this is a point here, right? So you can say these potential difference plus losses. And the losses, if you remember, it's a function of V squared over 2G. If you talk about eddy losses, K V squared over 2G. If you're talking about the friction losses, is FL V squared over 2G. So which means that V squared over 2G times this value here, right? So in this case, the system is becoming, to overcome the static difference between the two tanks plus overcoming the friction. So this is to overcome lift, and this is to overcome all losses in the system. Okay. So this is basically what. Okay. So in this case, we can draw this relationship, right? So we have this. So if you put a relation here, this whole thing can be changed to Q square over area square times 2G times summation of FL over D plus summation of K. Right? You can put this equation as a function of, static lift, or the difference between the tank A or 1 and 2. And then some, all these are fixed. All these numbers here are fixed for the same system, same piping, same diameter, same, coefficients and stuff like that. And Q here will be the variable. So you can actually draw this relationship here. So this is H of the system, and this is a Q, right? And it looks like, this will be H static total, as I said, plus K, or like a constant times Q squared. So which means that this whole equation will be converted into something like this, because it's second degree order, because this Q squared. So the H system and Q will be a curve like that. Okay, so for any piping system, you are expecting to see a relation between the head of the system, the head, like total head inside the system, and Q square is going to be a curve from a second degree order equation, right? So, and in this case, you can put this system curve into the pump curve. So you have, let me just add here one, just go over this by step. This is H and this is Q. We know that for the pump, this is a pump manufacturer, right? This is a pump curve, and this is coming from the manufacturer, right? Is that C? Yeah, C or constant. Just, I don't want to call it K, so I'm not confused between the K and inside the eddy losses, right? Any constant, right? A or B, or right? So this is a constant. Okay. So for this is a pump curve that is coming from the manufacturer, and if you draw the relation between H and Q on for the system on the same graph, so this will be, this is a system curve for a certain piping condition and losses and stuff like that. Okay, so which means that if this pump put on this system, where is the flow rate that you're gonna see running inside this system? The intersection, right? So this point here, right? So this will be the operating point. Can I run the flow rate here? Can I run like this? Can I go like this? Oops. Can I run at a higher flow rate? Can I get higher flow rate from this pump? For these specific conditions, can I? Why? Because the pump here at this condition here, the pump here can provide only this head, but the system need this head. You see here, right? So the system need more than what the pump can deliver. In this case, the pump will never get you a flow rate like this. And that's why we call this is your maximum flow, right? Right? So this is your maximum flow rate. Can I run here? Can I go like this? Of course. How? How can I run here? How can I decrease the flow rate? Huh? How can I decrease the flow rate? Anyone? No, don't touch the pump. Let's assume the pump is running at the same speed, everything. Yeah. That's not, yeah. Yeah, no. Increase the losses, right? Right. This is very interesting. Increase the losses. How are you going to do this? If you, okay. Simply think simple, okay, guys. It's not very complicated. How are you going to decrease the flow rate if you open the tap in the water in the morning? How are you going to decrease the flow rate? Use a valve, right? So just, the valve at the exit, just close it a little bit. By closing the valve, you are increasing the losses, actually. You are changing the system, because this system, you remember, this system is a function of K, right? This K here. If you have a valve and you're increasing the valve, that means you can just do this. You can actually make this system new system closing the valve, right? Right. So in this case, you can operate here now. Okay. So decreasing the flow rate in the pump is easier, right? So this is no problem, right? But increasing for the same speed, for the same pump, everything, you cannot do anything. If you want to increase this, if you want to achieve this point here, what you want to do in this pump here? What are you going to do in this pump? So this is a pump running at this RPM. If you want to increase, if you want to operate here, what are you going to do? What do you think you can do in order to operate at these flow rates? Now we can change something in the pump. What are you going to change in the pump? Maybe power. Yeah, but you don't change the power in the pump, right? You're not going to give the power to the pump, right? What you're going to do is basically, I mean, like touching the pump mean like you can do something to the pump. No, the valve is open. Yeah. Decrease the friction. You cannot decrease the friction. I was just saying this some time ago here, right? If you increase the RPM, right? So if you increase the RPM of the pump, okay. So if you are getting another, the pump operating at a higher RPM, so this is N2 is greater than N1. So you can actually, increase the speed, increase the RPM of the pump. So in this case, you can achieve higher flow rate for the same system. Okay. So this is what is, this is what is telling you about the system curve and the operating points. Again, also the efficiency of the pump is, at any point that you are operating between the system. This is your operating point. If you change the system, right, you can change the operating point of the system by, introducing more losses in the system. Like, for example, when we did for adding the valve or closing the valve a little bit. The efficiency curve sometimes is given like this, right? So in this case, if you need to find out the efficiency here, you just go and find out the efficiency of the pump at this point and so on, okay? Let's solve a problem here so we can get a sense of what the problems, at least at this level of discussion. So we have a pump like this, and this pump is this information provided by the manufacturer. It is a 32-inch pump. So 32-inch pump mean for this curve here, this is our curve. This is our pump that we are operating. So 32-inch pump, this is your impeller that you are using here, right? Operating at 1170 RPM. So this is a curve, or this is a chart for these operating conditions. The water here at 60° Fahrenheit, from one reservoir to another, 120 feet higher. So reservoir A is low level, and reservoir B at 120 feet higher than the first one. Through 1,500 feet of 16-inch inside pipe diameter with friction factor is given, right? So I have a simple system here. This system is and this pump is driving the fluid into another tank. And this level here and this level here, this difference is 120 feet. And the length here, the length total is 1,500 feet. The diameter is 16-inch. Friction factor is 0.03. Okay. He's asking what will be the operating point and the efficiency. So you just need to find out Q and efficiency of the pump at these points. Okay. So this is our pump, right? So it looks like you have options. This is your system curve. And the pipeline here is given length and diameter. No information about the eddy losses. That means eddy losses is not there. Like we don't see any eddy losses, right? So in this case, I can start by first neglecting any eddy losses. And, now if I want to get the system, so this is 0.1. And this is 0.2. So for the piping system, okay, energy or Bernoulli equation between 1 and 2, this will give you the system curve, right? So in this case, B1 over gamma plus Z1 plus V1 squared over 2G, right? And so this is the energy 1, and then minus energy 2, B2 over gamma plus Z2 plus V2 squared over 2G, right? Plus H losses between 1 and 2. This will give you your H system, okay? So the system that you are running here is between this condition here at 1, condition at 2. I mean, H system here is, this difference here is, if you remember, at 0.1. This is a level, this is a level, right? So in this case, so we have H system here is 120, right? So plus H losses, and H losses here is F L over D V squared over 2G. Okay, so system needed to overcome this static lift. Okay, so we call it the static lift. And please, if you remember this, and just to save time every time you are solving this type of problem, the system or the piping system head is equal to H static total plus this value here, which is, I can put it in terms of KQ square. So I can say that FL over D times 2G, right? And then times pi over 4 D square, all this, and this is going to be Q square. So I can put this whole, thing as in this case. So H system will be H static total, right? H static total, in order to be efficient in solving this type of problem. So choose like H static total will be the delivery minus, the suction. What is the delivery? This is a suction tank, and this is a delivery tank. So all the time, just use the same thing. Use the same kind of, process every time. Every time you see what is the delivery side, static head, minus the suction side, static head. So in this case, it is a positive because the delivery is higher than the static, right? So by 120. So I can say that, for example, here, H system is H static total, which is 120 feet, plus, all the values here, Q square. And then I can put all the stuff here. So this is 0.03 F times L. This is 1500 feet. The diameter here is, I'm going to put everything in feet. So it is 16 inches. So I divide it by 12. This will give it a feet conversion, right? Times pi over 4, the diameter square, which is 16 over 12. This will give it feet square. Is all area square, right? Times 2 times G, which is 32. You can just let me put it here. This is 2 times G 32.2 times all this. So I'm converting everything in feet here, right? So everything here in feet. So in this case, I can say that H static is 120 feet plus 0.269 Q square, and Q in this case here, this Q here is in feet cube per second, right? Remember, because we have to make sure that the units is correct. Unfortunately, in this case, because this graph here is given in gallon, right? And in order to find out the operating point, we have to plot the system curve on the same curve of the pump. So in this case, I have to really use gallon per minute, right? So we know that, Q gallon per minute is equal to, or sorry, the opposite. Q, so feet cube per second is equal to 448.8 gallon per minute. Okay, why I'm doing this? Because basically in this equation, this is your system curve. If you remember from our discussion in the last few slides, we need to get the operating point, and the operating point is, the point that is intersecting between the system curve and the pump curve. We have the pump curve here in, feet and gallon per minute. So in this case, we have to really convert everything in, gallon per minute. So what I'm going to do here in this case, I have see here, this is 4, 8, 12, 16, 20, 24, and so on. I don't want to have to really go all the way, right? I can just get in, at Q is 0. This is Q, H system. Oh, sorry. Let me do this. Q, gallon per minute, Q, feet, Q per second. Okay. H system. Okay. At 0, right? H static is 120, right? So in this case, so I will have, it's actually below here, right? I don't need to get into like 0, but what I'm saying here is like, if you want to plot at 0, you will need, like, you know, on the H static total 120. At 4, this is full gallon per minute, just convert it into feet cube per second here, multiply by this, right? And then get H static, right? I didn't actually calculate all this. At 8, you convert it to feet per second here first, and then you put it in this equation here, so you can get H static total, right? Just a way of converting, you know, between the value in the charts where you need to plot, and the value in the equation, which is in feet cube per second. Okay, so you put, like, you know, the values here at 10, you know, I think, or 12, sorry. You can choose whatever numbers here, it doesn't matter, right? You just need to plot this system on the charts. So what I did in my case is, this is a point here as well, like this. So it was something like this. Okay, so the system curve that we are plotting, this is your system curve, is actually because it's, is it 20? Is it, oh, it's 32. Because this is our pump that we are dealing with. So let me just change this, just to change everything. Right here. Okay, it was something around here, this point. Okay, so a system curve, we plotted using the system equation. Okay, we plotted on the pump curve, and we are getting the intersection point. This intersection point is actually, you know, the Q of the operating here is 1500 gallon per minute. So let's see here, this is times 1000, so it's about 15 here. This is about 15 times 1000, so it's 15. All right. And the efficiency is very close to the 82%. So efficiency of the pump is 0.82. You can say 0.82, 0.18, something like that. If you want to say that this is 1.8 or something like that. Close number is okay, like, you know, it doesn't have to be exact specific point, but of course within a certain range. Okay, so this problem is the first type of problem where you just need, you have a system curve, you have the information about the piping system, you plot the piping system, you put it on the same chart of the pump, make sure that you choose the right pump, the right, you know, RPM, for example, in the market. If you are searching on the internet, for example, for a specific pump, when you are searching for what pump that you need to buy or purchase, right? And then you draw the system curve on that chart, and then find out your operating point, just to make sure that this is a flow rate that you are designing for. Okay, of course, this problem is straightforward. In giving you the exact chart and giving you the exact system, you plot both together, get the intersection point to find out your operating point and efficiency of the pump. the curve, the system curve here. You remember the discussion we are talking about here, right? So we need to get the system curve, right, and put it on the pump curve to find out their operating point, right? So I have in this problem, I have the pump curve, and he's telling you from this manufacturer, use a 32-inch diameter. So this is a 32-inch diameter pipe. So this is your curve of the pump. And he's giving you information about the system that is 1,500 feet, 16-inch diameter, the friction factor, right? So you have an information about the system, right? Which means that you can develop a relation for the system curve. So this system curve, when we discuss it, right? So at the end, the system curve is your H static total, the head of the delivery minus the head of the delivery tank minus the head of suction tank. We call it the H static total, plus, you know, for example, in this case, we don't have AD losses, we only have friction losses. So which means that only this term here, right? So I'm putting all this equation as a function of Q square, right? So in this case, I get this, you know, all terms at the front of the Q square, which is, I call it constant. Why constant? Because diameter is constant, length is constant. Everything in the piping is not changing with the flow rates, right? You move a flow rate that is that much, same piping, same diameter, same everything, right? So we call it the constant or the system constant, right? So in this case, H system become something like this. So this is a system here is equal 120 feet plus some value Q square. So this equation now, in order to find out what is the operating point, we have to plot this equation, right? The only difference here, this equation is Q in feet cube per second, but the chart is in gallon per minute, right? And we are interested to plot the curve on the chart in gallon per minute. So in this case, you have to make sure that you are converting this, right? So at 4 gallon per minute, I need to find a point, right? So just, you know, this 4 gallon per minute converted first by multiplying 448.8, you convert it to feet cube per second, you put it here in this equation, you get H system, and so on for 8, 12, and right? And now we have a relation between, for every single point, you have H system, right? So for 0, you have this, for 4, you have this value, right? So these values here, right? You plot the curve. So you plot this system curve here on the same map, on the same chart. Okay. 448. Yeah, sure. I believe you guys are gonna do a much better job than me. It's just plotting this, right? But you know, that's the idea here. Just trying to plot this equation on this map, right? If you are precise enough, sorry about that, but you know, I didn't pay so much attention to like even looking at the chart. But draw this curve. Once you draw this curve and you intersect between the system curve and the pump curve, right? You are getting, you know, a point of operating point. Get this operating point in terms of Q and in terms of efficiency. Efficiency here is about 82. This is 78. So efficiency is somewhere here, right? Okay. So I forgive you if you are making mistakes. So please do the same for me, right? But it's a very straightforward thing. And, you know, luckily that this is basically the exercise that you're going to do in real life when you are actually designing a system where you have a piping that you know exactly the information about this piping, and you want to get a pump that is reasonable to get a certain flow rate, right? So you know exactly if you buy this pump and you put it in this very specific system, what flow rate is. Just converting factor, I think. Yeah, getting into the details. Okay, so this equation here, everything has to be feet, you know, feet and seconds, and right. So you're gonna use like feet square per second to calculate HS. Okay, so now for this chart, you only have gallon per minute. Okay, So if you want to get a point at 8 gallon per minute, how are you going to do this? You convert the 8 gallon per minute into feet square per second, right? So you multiply by 4,480. Sorry, this is 8,000, right? This is 8,000. This equation here is multiplied by 1,000. Okay, because these values here is 8 times 1,000. So 8,000 gallon per minute, you convert it into feet cube per second, right? Once you convert it to feet cube per second, you put it in this equation here, right? To get HS in feet. Okay. I hope I am not messing the main purpose of the questions, because to me, this is very, you're graphing like a data points on a XY plot. I would expect to max flow rate. Okay, Trevor, I don't know. The intersection would represent the maximum flow rate. Yes, on the x-axis. Or maybe I did wrong. Sorry, I'm yeah, I know what is somebody when I speak on the mic. I guess you please do this. I think I'm mixing between the H and the Q when I look at these charts. The flow rate is 4,400. It's 15,000. So my point is here, right? It's about 15 or maybe a little bit here, right? Okay. So this is a flow rate here, right? And HS, don't remember, HS is 430. Yeah, sorry, H system. So at this point here, this is H system is 430 feet. Does it solve the problem here? The people are very interested in the numbers, missing the point. Okay, I know a number is very important, just to make sure that you are buying the right bump, right? But I guess you understand what I'm saying here. Please confirm. You understand the point of this problem? Aside from the accuracy of the plot and stuff like that? Okay. Okay, guys, how about that? How about, I'm not going to give you a number. I'm giving you approximate number. I can't really switch between my glasses and then look at the numbers here I'm getting. So if this values, let me see here. Okay, if I do the intersection and becoming here, this is a point here, right? So now I need to find out this line of efficiency that is representing this point. So now I have a line that is, this is 82, right? So this line here is 82, and this line is 78. So it's going to be some line in between here, right? So if I look at here, this might be something just smaller than 82%. Okay. So in this case, I can say, for example, if this point is here is about like, this is 80, this is 80, this is 80.5 or 81, something like that, right? If you say 82%, I'm fine too, right? Okay. Let me ask you the question again. Did you get the idea of this problem? Okay, aside from the small little difference on the chart, of course, it's going to be some accurate. Like if you have more time to really plot exactly those lines and get the intersection right, you'll get the right number. But that's basically the idea. Okay. Okay, so let's jump into something, another important feature in the pump, or the hydraulic hydrodynamic pump, or the centrifugal pump as an example that we take in this course, something called net positive suction heads. right? You remember when we were talking about this type of pump, we have like, the impeller rotating and we having a suction, like, you are decreasing the pressure at the inlet of the pump. So you are making a certain suction effect to move the fluid inside the pump, and then you are increasing the pressure inside by the centrifugal forces or the centrifugal action of the pump, right? So you have to make sure that when we are using this pump in a system and you are decreasing the pressure in the inlet of the pump, you are kind of, avoiding any evaporation of the fluids, right? You remember the most important parameter that we discussed in the first chapter, something called the vapor pressure. The vapor pressure is the pressure at which the liquid become vapor, right? And you don't have to really increase the temperature, but you can decrease the pressure, right? And we talk about something called cavitation at that time. And the cavitation is when you have vapor in the liquid and now this vapor goes to a higher pressure point, the liquid kind of collapse, and then the liquid jump into this cavity and then hit the equipment casing or something like that, right? So in this case, we're trying to avoid cavitation because those can basically damage the pump material. So and that's why for every pump is going to be some kind of operating point that will allow you to judge if this system at this operating condition and this pump is operating in this system, is it going to have any cavitation or not, right? And that's why we call, there's going to be a problem, a definition called net positive suction head. I see the time here is approaching the final, but let's just make the definition here and then we can solve the problem next time. So net positive suction head is basically the head required at the pump inlet to keep the liquid from cavitating or evaporating, right? And the pump suction or the pump inlet at the suction here has a lower pressure point. Why? Because the fluid is going inside the tank, inside the pump from this tank. So you have first, you have a certain level of energy from the tank one, minus the losses, right? Minus some value of, for this pump, because the pump is driving the fluid with a certain velocity. So if you look at this, right, there is something called net positive suction head available in the system and net suction positive head available required by the pump, right? So let me just go here first, and then we'll come back to the first slide. So you have a pressure at the tank, at the level of the tank. So imagine you have a point now at the top of the tank. So the pressure here is atmospheric. Remember, when we are talking about vapor pressure, we are talking about absolute, scale, because vapor pressure always lower than the atmospheric, right? So it has a negative value, or right. So every time we are talking about vapor pressure, we are kind of referring to this value in a vacuum term, which is lower than the atmospheric by so much, right? So in this case, we have to keep in mind that we have to use an absolute, reference in order to solve a problem related to net positive suction heads for the pump. So you have the pressure of the atmospheric minus the potential, because this is the head, and then minus this potential here, minus the losses in the, the inlet side, right? And then will be equal to a vapor pressure. So you're trying to avoid having the pressure just before the pump that is equal to B vapor, right? And we call this is basically, the net positive suction head available by the system, okay? Friction here is the friction on losses between the reservoir and the inlet of the pump. Z here is the pump location versus the level of this tank, right? So where is the pump is located. We have to make sure that as we are reducing the energy, we are reducing the pressure as well. So we are not getting to the point where the pressure become B vapor, right? So as if this term here is BA over rho G minus ZI minus H losses inlet is equal B vapor or, rho G, right? As if this has to be greater than B vapor or BG. Or the difference here we call it the net positive suction head. So this term here minus this term here will be the net positive suction head available in the system. Okay. Now the pump will provide you with what is required by the pump. So that's why when you look at this curve here or the chart of the pump, you will see net positive suction head. So this net positive suction head here, this is a manufacturer, value given for the pump. Okay, so you have to make sure that whatever available in the system is higher than what is required by the pump. So the system has higher pressure than what is needed to evaporate the fluid in, at the inlet of the pump. That's why this net positive suction head, category or criteria is very important to check when you are selecting the pump. Okay. And that's why in this slide is telling you that you have a net positive suction head available in the system, which is you can calculate based on this equation, right? And the required here is, provided by the manufacturer. In order to avoid cavitation, this net positive suction head available should not exceed the net suction positive suction head required by the pump. Okay. So next time we're going to apply this principle in order to check if this pump is going to cavitate or not. So I'm going to stop here and I'm also going to stop the recording. And for people who are interested to stay around for any question, I will be happy to answer any of these. Let me stop recording.